Okay, if I can have your attention, guys, my friend, thank you. I usually redraw this. This time I made a copy for you. I apologize, it's small, but it's going to be in a PDF for the network that you can look at it. This will cover chapter 12. Chapter 12 talk about transformers, guys. So what I did for you, I drew a couple of transformers, and I know it's busy. Just to explain the power systems, every power system that you're going to encounter, some type of a transformer at the beginning of that power system. So here's what I did. I went into, there's two power system, guys. You call it low voltage service. 99% of the time, you're going to be looking at low voltage service. You're going to get the low voltage. This one is the one that says December 20th, 2011 on it. So you're looking at low voltage service right in here, less than 600 volt, and these are, I listed five different transformers, Again, this is the sheet. This is the sheet, guys, that says at the top December 20, 2011, right in here. Oh, they all do that. Okay. See all the transformers at the top looks like this. Okay, so I threw this for you guys just to show a few things and where would we use these power systems. So first of all, we have 5 power systems. All start with a transformer. All these power systems always start with a transformer. The first power system, guys, you are very familiar with because this is the 24120 single-phase system. Hot 1, hot 2, neutral, right? That's what we did for the residential project. You should be very familiar with that one. So I have a transformer on the secondary side, hot 1, hot 2. I have a neutral. On the primary side, most likely you're going to have 7200 volt, most likely. It could be 2400. The primary side is a high voltage here. The secondary side is your service. H1, H2, most likely it's going to be 24120. Where would we use this? I always say this is mostly residential, light commercial, and up to 800 amps, though you might get it for higher than that. So that's kind of give you an idea where this system is commonly used. Where is this system commonly used? Single phase, as you can see, residential, almost always residential, almost always light commercial buildings. Can I use it for industrial? Yep, but it's not a good idea. Any question, guys, about system number 1? 24123 single phase system. Any question about system number 1? So that's where system number 1 is. System number 2, if you look at it here, Nick, my friend, it's a delta 3-phase. Can you guys see delta 3-phase? The first delta, the primary, is 13.8. That's typical, 13,800 volt. The secondary side is 24120, except it's 3-phase this time. That's the only time, actually, you can get a 120, 240 3-phase system is by having a delta on the secondary. And the center tab, they call this one, can you guys see that little here, center tab? So you got 3-phase, commercial, light industrial. Please don't hold me accountable to the amps. These are typical, up to 1600 amps. Typical, can I get them for more than that? Yep. Where did I get these numbers? Experience. Where would we use a system like this? This is the most important thing, guys. Where would we use it? If you have 10% or less is single phase load. Where would you use a delta center tap system in a building? Typically, if your load, single phase load, is 10% or less. For example, I always use a pump house, a water pump house full of pumps, 24 volt, 3-phase pumps that pumping the water to the city. But inside is just a house full of pumps, pumping from the wells and pumping it all the way to the cities, right? Now you need to power them with 3-phase 240, but inside the house you need a couple of convenient 120 receptacles on the walls and convenient couple of lots that you're burning them at 120. So these are small chunk of single-phase loads. That's where would a system like the second system would make sense. 3-phase, commercial, light industrial, 16,000, that's the application here. and 10% or less single phase, it makes sense to use this system number 2. Any comments, guys, about that one? Any comments about system number 2? System number 1 is residential. System number 2, mostly commercial, industrial. No residential. You never see a system number 2 in residential. Delta, delta. System number 3, guys, is the system number 3 and system number 4. 3 and 4 is the most common ones. If you look at 3, you have a delta on the primary delta, or the secondary Y. It's 28120. That's a system that we're using in this project, right? System that we're using in this project. Three phase. Don't forget that this is going to be a grounded system. You have a ground here. So grounded system. This is system number 3 is the one that we're using in the primary 13.8, on the secondary 208.120. It's a 3-phase system. Residential, commercial, light industrial, you can get the system up to as high as you can get, 4,000 amps. Most likely they don't go higher than 3,000 amps, but you can get it as high as 4,000 amps. Now, where would you use a system like this, Phil? I have been told, and from what I've seen, is if you take the square foot of the building. If your square foot of the building is 15,000 or less, 15,000 square foot, it makes a lot of sense to use a 28120. What are the other options? The other options too is 48277, which is system number 4, 48277. So the third system is very common, guys. Again, residential for high risers, commercial and light industrial up to 4,000 amps. Does that make sense? How we're going from a smaller system up to a higher system? System number 4, my friend, is the same as system number 3, except to start with 48277, the same thing, 3-phase, heavy commercial and industrial. I emphasize the word heavy. You have heavy commercial and industrial buildings, almost always 48277. Almost always done with it. 48277. Then we transfer it down to 28120 so we can burn some lights and burn some receptacles. I highlighted system 3 and 4 since we're commercial. 3 and 4 are 95% of what you guys will be encountering in a commercial industrial building. System 3 and 4. That will probably 90 to 95% of what you're going to see in any building, either 28120 3-phase or 48277 3-phase. Transformers sitting outside. All of them are Y. All of them are grounded. Very few times we get non-grounded in a system. All of them are what they call a 4-wire, 3-phase and a neutral. Any question guys about especially system 3 and 4? Especially system 3 and 4. Since we're commercial industrial, 3 and 4 is your baby. System 3 and 4 is your baby. For 4, I say that these are, the green stuff is opinion. Please don't hold me accountable. I can't go to court defending it. Heavy industrial, heavy commercial, and industrial. Most likely you're going to go for 8277. If you have a building, square foot of a building, more than 15,000 square foot, that's a good idea to ask for 48277. That's a bigger building. 48277 makes sense, but doesn't have to though. Any question about 3 and especially 3 and 4, because these are delta Y transformers we typically get into any commercial industrial building. The last system, system number 5, these are, I call it the Canadian system. This system actually, though we use it here, it takes a primary of 13.8. You can have a 13.8, 13,800 volt on the primary. On the secondary side, it's 600/347. High voltage in the secondary. So where would you use system number 5? System number 5, not commonly used, but that's very heavy industrial plants. You can run them at 600 volt. The higher the voltage, guys, the better, the more efficient the system is. Everybody knows that? The higher the voltage that you run a building at, the more efficient the system is, the more powerful, the more capable the system is. But what's the drawback? The more dangerous the system is. You put 600 volt across two in a panel like this and ask Ashley to work on it, you arc flash that panel, you can kill somebody, versus 28120. So the higher the voltage, more dangerous, but the higher the voltage is also more efficient. Higher voltage, guys, always think of it as smaller conductor. Smaller conductor, smaller conductor, and also higher voltage, less voltage drop, because now you can take at, just to give you an idea, like 277, I can put close to, what did we say, 18 lights when we did our math. We can put 18 lights like this on 120 amp circuit that's burning at 120. If you burn the same light with a different ballast at 277, you can almost put twice the amount of lights. Same wire, the same overcap protection device. So you have a 20 amp. Instead of 18, twice of that will be 36, right? 36 fixtures like this you can put on a 20 amp circuit if you burn this fixture at 277. Is that a big deal or what? Am I the only one who's excited? No? Do you see how the higher the voltage, the better the system is? Any question, guys, about these? That's my always thought of low voltage. I call them low voltage services because the secondary side that you're looking at right here is all low voltage. Any question, guys, about the low voltage services? So any building that you walk in, Phil, it's either going to be 28120 or 48277. You might encounter from time to time 600 to 347 volt buildings. Not a whole lot of comment. And the same thing. So number 2 is rarely used, not a whole lot used to. And number 1, of course, residential. Mostly residential, light commercial. So I thought just to throw these power systems, so you guys, as you start designing your building, the first thing you need to understand is what voltage system are we going to be using it. The mechanical engineers are going to ask you, we're going to buy a chiller. What voltage do you guys want to burn these chillers at? So you have to decide the voltage system. If you don't know how to decide the voltage system, here's your only 3-phase. Now we're talking about commercial building. You have 3-phase, either 2H, 120, or 48277. The decisive factor would be the square foot and how heavy. If it's industrial building, always 48277. If it's commercial building, look at the square foot. Office building, more than, this is rule of thumb, more than 15, 48277. Less than 15, 28120. Is it wrong to put less than 15, 48277? No, but that's kind of a rule of thumb. Any questions about these systems? Again, this is PDF on the network for you, because I know the print that I gave you is not clear when you do a 3-in-1. Any question, Tom, my friend? So I'm going to emphasize the word low voltage here, low voltage services. Low voltage services, if you look at the voltage, 600 volt or less. Low voltage services, 600 volt or less. Now I'm going to go move into the high voltage service. And very few of you guys will be working. Any question about the low voltage services? Phil, does it make sense, these 5 systems that I can use in any building? And what's the best way of using any of these systems? So what's the rule of thumb? Higher voltage, more efficient system. But at the same time, dangerous system. You have to find the happy medium between which system. And I gave you a couple of rule of thumbs here where systems are typically used. Any questions, guys? Any questions? Okay, now Ashley, these are low voltage services. How about high voltage services? Can I bring 4160 to Dunwoody, burn the equipment at 4160 volt? Yep, if you justify it. They call them prime service. The second one, the second slide, which you guys have it right underneath in the same sheet that I gave you. This is, I want to emphasize the word high voltage services right here, higher than 600 volt. Higher than 600 volts. So building like the U of M, 3M, Mayo Clinic, these are multi-campus buildings, guys. Multi-campus buildings, they just because the load is so big and the distances are so far of the buildings, it justifies using higher than 600 volt system, higher than 600 volt system. So here's a higher than 600 volt system. typical higher than 600 volt system. Actually, there's a transformer sitting right in the back of your building. This transformer, they're bringing 60,000 kVA to that transformer, 69,000 volt to the building. That's a lot of voltage, 69 or 150. Typically, the primary transmission line, Rob, they're bringing 69 or 115 to the transformer. This is the primary. This is the utility side. Your side, the side you own and operate, is going to be the run at these voltages, typical in the US. 2.4K, 2400 volt, or 4.16K, 4160 volt, or 13.2K, 13,200 volt, or 13.8, 13,800 volt. This is your service. This is your service. So what you do, you take this 13.8, for example, very commonly used, switch gear coming out of this transformer, and you have 5 feeder 13.8 coming out of one transformer. You know, you take the feeder here, you put the feeder into a switch gear, medium voltage switch gear, and you take 5 feeders. Feeder number 1, 13.8, let's just say 600 amps going to building A, and the second one building B, C, D, and E, and so forth. So 1, 2, 3, 4, 5. 5 feeders going to different buildings. So that's how it probably would look something like this when you 1, 2, 3, 4, 5, that's 5 feeders, and all these guys inside a switch gear, inside a circuit breaker or a fuse switch gear, and the switch gear is 13.8 kilovolt, 2000 amp. Let's just say 2000 amp. And can you guys see that? 13. You bring the transformer to the switch gear like this, 2000 amp, typical 13.8, and then each one of these feeder will be going to feed a building. So high voltage. Again, where would you encounter this? Big campuses, big industrial plants, refineries, oil refineries, all these campuses that need a lot of power. You of them have their own 13.8 system that they distribute. Then, Nick, at the bottom here, what they do, you take one feeder, you land it on a transformer like this, and that's where you get 13.8, 480, 277, where you feed your building. You can't bring these lights at 4160, guys, 4,160 volt. You can't. So what do? You take the feeder to another transformer, strip it down to most likely 480, 277, and feed it through your building. Feed it through your building. Any question, guys, about the primary service or high voltage service versus low voltage service? So I thought I threw these at you from the get-go. So every one of these feeders can get you up to 4,000 amps. Where would we use things like that? Multi-campus buildings or businesses, very heavy industrial. They take 4160, 13.8 or 13.2. Any question? Any comments? Probably very few guys of you would be working on this. Yeah, I mean, 95% of the buildings that we design, actually, 95 is going to be low voltage, 600 volt or less. Comments, questions? Any comments, any questions? Okay, now, having said that, you can tell why Chad wants you guys to know these services, because now we're going to go have a transformer, a big fat transformer, and we need to size the following. And I give you this one too, guys. Question number 1, you have it at the bottom. That diagram is there, the same page. I have an example, 100 kVA transformer. Can you guys see that? Everybody have it? I have a 100 kVA transformer. The primary is 480, and the secondary is 208, 120. And I need to find how many things? 5 things. 6 things for this transformer. Typical. Now, I picked the 480, 208 sides, right? But the voltages, you're going to see we're going to use different voltages. Any question about what we're doing here, guys? Now, we took a service, or separate derived system, and we need to size 6 things for this service. That's your job as a designer, to come up with a size. If you can look at the first thing you need to size, guys, is the conductor, the primary conductors, the primary fuse, then the secondary conductors, the secondary circuit breaker. Then we have the grounding electrode conductor, and then the main bonding jumper. Everybody knows what this means, that main bonding jumper. And that green thing is a box of a transformer. Any question, guys, about what you see in front of you? And I gave you the picture so you don't have to draw that. Everybody can see it? Let me go over it one more time. I have a transformer that's running 480, delta primary, secondary, 208, 120, 3-phase, obviously. I have 4 wire on the secondary because it's a Y, 3 wire on the primary because it's a delta. And I need to find the fuses and the conductors on the primary, the circuit breakers and the conductors on the secondary, as well as the main bonding jumper, as well as the grounding electrode conductor. Any question about this? Any question about that? That's what we're going to be doing. To help me with this, Ashley, I'm going to go, guys, and flash a couple of things for you before we go ahead and start. So let's go to the NEC code and the article that talks about the transformers, right? So that will, I mean, if you're talking about transformers, it will be better to go to the transformers, right? So let's go to the transformers and look at very interesting and very important table. Okay, there are 2 tables, and we looked at them, I believe, before, guys. If you don't know these tables, you must pay a lot of attention to these 2 tables. Okay, let's look at this. I have a transformer. This table is 450.3b. Very interesting, 450.3b. This will size the overcurrent protection device of the transformer. Overcurrent protection device of the transformer. The most important thing about this table, we're looking at page, here's the page, guys, 349 in the NEC code book, 349 in the NEC code book. Okay, everybody's there, 349, page 349, table 450.3b. Okay, the most important thing about this table, guys, is right in here. If you have a system, the voltage is equal or less than 600 volts on both the primary and the secondary. The primary and the secondary. So if you have a transformer where the primary and the secondary voltages are less than, the primary and the secondary voltage are less than 600 volt, then you use this table. The primary and the secondary. Let me give you an example of that boy. Where am I going to put this one? Here's a transformer. Right? This is a 480 volt, and from this side, 208/120 volt. Does this table apply to this transformer? Does this table apply to this transformer, and why? Yes, because the voltages of both the primary and the secondary are less than 600 volt. Okay, so that's the rule number 1. Second thing you need to apply to is primary only protection. Your default is, you always default to primary and secondary protection unless you know otherwise. Always default to primary, and you have a fuse and circuit breaker both on the primary and the secondary. Okay? Then, here's your primary protection. This is your secondary protection. A couple of things. So let's say most of the time, current of 9 amps or more. Most of the time you are in this area here. So your amps are more than 9 amps or more. We're talking about power transformers. Most likely, they're going to be higher than 9 amps. These are current 9 amps or less. These are very tiny little, almost controlled transformers that you can use, right? Very small transformers. Okay, so if you have if you have more than 9 or more, as this will say I equal or this is I like to write it I more or equal to 9 amps. This is right. Then what's my multiplier? 250. You take the full load current on the transformer and you multiply it by 250%. 2.5. Okay. If it's not a standard, you need to go down. Why do we go down if you don't hit a standard? Because it doesn't tell you to go up. If you read note number 3, it doesn't tell you nothing. It doesn't say anything about going up. Okay, so here's my transformer. When I size the primary, here's my primary fuses here. Then I'm going to be right in here. Any questions about this? So if I have your default is primary and secondary protection. So what do? You take 2.5, you take the 2.5 multiplied by I primary. And then if it's not a standard, what do? Go down. If you decided to use a primary protection only, meaning nothing on the secondary, which we use it under certain circumstances, look at what your multiplier is, 1.25, okay? We're going to just go to the default. The second thing is I want to take you, so that's where these things are peanuts, so I don't even like to mention them. Look at the amps are smaller amps for small transformers. 99% of the time you're not going to encounter them. Okay, the second default in this table is the secondary. Secondary, the same thing as I. We are defaulted here because I is more I secondary. This is I primary here. I secondary is more than 9 amps. I don't know what's with this 9 amps. Makes it so interesting. 9 amps current, more than amps. What's my multiplier? 1.25. 1.25 times I secondary. If it's not a standard, go up. Why do I go up if it's not a standard here? Can you guys see note number 1? If you read note number 1 here, somewhere here, next, right in here, next standard should be used. If you guys read it, if you hit a non-standard, you can go to the next standard. That's why I went up here and I went down here. And right here, 3 guys doesn't tell you to go up. So what do? Either you custom design yourself a fuse, which is cost you an arm and leg, or you're going to go down. Any questions about this table? Very, very important to know how to use this table. Very important to know how to use this table. Any question? So the question that I would ask is, your default, you're always almost defaulted to this situation, right in here. That's your default. Now, under certain circumstances, guys, you can size a transformer to feed a load with no secondary protection. So these are my fuses, by the way. This is where my fuses are, right here, and right here. This is my fuses, right? That's how I size them. And everybody knows where the I primary. Here's my I primary here, my I secondary here, and we size the fuses based on this, I primary, I secondary. Okay, the last thing I want to say is about this. If you use primary protection only, then look at this, no protection on the secondary whatsoever. Then look how your multiplier becomes 1.25. Where would I use something like this? You have a transformer dedicated to a piece of equipment. That might be a good no panel, not landing on a panel. Transformer going, feeding a piece of equipment. That would be a good application. Not a whole lot commonly used in commercial industrial. Again, your default is going to be the bottom. So I'm going to do examples on the bottom, the most default one. Any question, guys? Any question about this? Okay, so these are what I want to highlight from this panel. Okay, so all right. Now, knowing what we know, let's go solve this problem. Knowing what we know, let's go solve this this transformer. All right, let's go ahead and solve this transformer. I have 100 kVA, and you guys have the picture, so I need to find the primary feeder. How do you find the primary feeder? We need the I primary. I primary equal, what's the 100 kVA? Divide this by, Ashley, the voltage on the primary is 480/277, 1.73. We all know 480. So find the full load current of a transformer on the primary side, no problem. And that will give me, if I did the math, that will give me 120 amp. 120 amp. 120 amp. Any question guys about this? Any question about 120 amp, right? Did you guys come up with 120 amps? Okay. That's a full load current. The second thing I would like to do is find the conductor. Now, if I don't know what the load is going to be connected out of this transformer, I have no idea. I haven't calculated the load yet. I assume if I haven't calculated the load yet and size the transformer, guys, always assume it's going to be continuous and multiply it by 1.25. Okay? So I'm going to find feeder size. Feeder size on the primary, of course. We're still on the primary. That will give me 1.25 multiplied by 120. If you guys did that, you're going to end up with 150 amp. And make sure you take this one to 310.15 B16 under 75-degree column. And that will get you at 3 conductors and 1 aught AWG. Let's assume it's inside, so THHN. Yeah.
Where did we get the KVA?
Given.
Is that or which transformer?
This is one transformer. Primary, secondary.
Okay. Oh, okay.
Right? This is one transformer. Can you guys see that? A transformer has a primary and secondary. It's the 100 kVA is for both the primary and the secondary. That's why I put them in the middle. Did they do the math wrong, Phil? Did you come up with a different number?
No.
Oh, 1.25. Well, the 1.25 is really it's sizing. How do you size a load for an amp? For a branch circuit or a feeder. For branch circuit or a feeder. You're going to take 1.25 if it's continuous. If it's non-continuous, 1.0. So
that was a 15 years.
That we're assuming it's continuous load. That's where your judgment is going to be. If you go to the article, guys, it doesn't tell you a whole lot about the feeder of a transformer. Talks a lot about the overcome protection device. Device installation. I could give you this if that will work for you. 215.2A1. That 215. This is for feeders. 215.2A1. That will tell you basically if it's continuous or non-continuous load. That's how we size it. Okay, if you look at that, because it's ultimately it's feeding a load. It's a feeder. 215.2A1. If you go there, we'll say if it's non-continuous load, 100%. Continuous load, 125. We're assuming it's a continuous load here. Okay, let's go to the overcome protection device. Now the primary overcome protection device. What was the multiplier for the primary overcome protection device? 2.5. So take this. Now for this one is from table 450.3b, right? 450.3b. That's we have a reference for this. You take the 2.5 multiplied by 120, you get yourself a healthy 300 amp. We hit the jackpot here, 300 amp. You take this one to 240.6 NEC, and it's a 300 is a circuit breaker or a fuse. And if it's not a standard, what do? Go down. But we happen to have a standard, right? 2.5 times 120, 300, right? If it's not a standard though, had we came up with 299, what do? We're going to go to 299, 175 is the next standard down. What 175? 250. What am I telling you? 299, the next standard down is 250. But in my case, we hit the jackpot and we're good. Any questions about this? Okay. The next, let me see it when you're done. Thumbs up, good, done, okay. Let's go to the next, guys. So we did the primary, let's go to the secondary side. We got that one here. Let's go to the secondary side. The secondary side, actually, my friend, is I secondary equal the same 100K divided by 1.73 times 4, oops, what's the secondary voltage? 208. 208. Okay, and if you do that like I've done, you came up with 278 amps. Okay, now the same thing. I'm going to use the same reference here. 215.2A1. 215.2A1. If you go to 215.2A1, this is sizing for feeders. Assuming it's continuous load, I'm going to take 1.25, multiply that baby by 278, and if you guys did the math, if I did the math right, 348 amps, okay? 348 amps. Then you take the 348 amps, take it to 310.15 B16 under 75 degree column, and that will get you a healthy, now, I know it's going to be 500 kcm, 500 kcm, THHN, we're assuming it we're inside, okay? Now, how many conductors? I know I'm going to have at least, how many conductors I need? At least 3 conductors for the phases. How about the neutral? Should I derate the neutral? Well, now if we're going to derate the neutral, we have to land it on the panel and we do the calculation slightly different. In this case, I'm going to pull a full neutral. So how many conductors then I need? 4 conductors. Could I have taken this neutral, Ashley, and derated it based on a 200 amp? Yep, I could have derated the neutral. For just because we're focusing right now on the calculation of the transformer, should I derate the neutral? I think it's a very good idea to derate the neutral. You know what? Let me just erase this. And let me derate the neutral because I really want to get you. Let's put 3 here, guys. And let's do the neutral. The neutral load, as you can see, is what? 348 amps. So I'm going to take the first 348 amps. Take the first 200, leave them alone. The remainder is what? 148 times this by 0.7. I need somebody, I don't have my calculator. I need somebody to do that. Derate the neutral. $200 plus 70% to 148. Anybody has a calculator handy?
303.
303 second.
304.
304. 304. 304 amps. Then you take the 304, 310.15 B16. What do you get? 75 degree column. 300, 400. I have 304. I didn't do the neutral. 350. Second. Do I have a second for 350? Yep, 350. So at 350 kcm, one conductor. Okay, so that's it. I just derated the neutral. I derated the neutral. The last thing I want to do, guys, right in here is number 4, which is secondary overcurrent protection device. Secondary overcurrent protection device. This is from 450. Table 450.3b. It says take the 1.25, multiply the 1.25 by the 278. That'll get you a healthy 348 amps. Then you take the 348 amps, take it to 240.6, and that will get you a healthy 350 amp fuse or circuit breaker. And if it's not a standard Oladipo, what do I do? Oops, I go up here if it's not standard. Thank you. If it's not a standard, I should go up. Done. That's the secondary conductors. Any questions about that? So we have 3 conductors, 500 kcm, 1 conductor, 350, and we size the overcurrent protection device 350 on this transformer, the primary. We're going to go do the bonding jumper and the grounding electroconductor quick, and then we give you a break. Let me give you a thumbs up when you guys are done. Done with that? No? Did you do make math mistakes? Anybody checked? I'm going to go size 5. 5 is the grounding electrode conductor, and 6 is the system bonding jumper or main bonding jumper. Okay. Grounding electrode conductor for separately derived system. I'm assuming this transformer is owned and operated by me, so I call it a separately derived system. I own and operate this transformer in my building. It's not the utility, so it's separately derived system. Now for this one, guys, I call this one grounding electrode conductor. You guys are very familiar with a grounding electrode conductor. For this baby, you need to go to grounding electrode conductor. You need to go to 250.66. I have 250.38.3. I think it's also 250.38.3. A3. Here's 3. Okay. Grounding conductor. Okay. All right. Bonding jumper, grounded system, or separately. This is for the system bonding jumper. Actually 5. They just changed the numbers here from 2011. 2011. This becomes 250.30A. They just changed the numbers. A5. They make it 5 this time. Well, if you have a separate derived system, guys, why do you go to 250.66, Ashley? Because this is not a main. This is separate derived system. Why would you go to 250.66? Because 250.30A5, a grounding electroconductor for single separate derived system, it will tell you to do so. Okay? So if anybody's questioning it, then, like any other grounding electroconductor, guys, we size based on 500 kcm. You take this one to table 250.66, and I got one conductor, 1 aught. It could be bare, insulated, or covered. Bare, insulated, or covered. Your choice. Bare, insulated, or covered. In a building like this, probably most likely would be insulated, guys, and identified as a green and going all the way to the grounding electroconductor. Ashley, did we do it right? Did you guys check? The last thing is called system bonding jumper. System bonding jumper, it's actually 250.30A1 system bonding jumper. A grounded conductor. Okay, so for system bonding jumper, you're going to go to these two articles. You're going to go to 250.30A1 and I like to refer to 3 too, 1 and 3. If you go there, guys, it will tell you to do what I'm going to be doing here. And also table 250.66. If you read this article, it refers you to this table and it tells you if it's higher than 1100 kcm. Remember that higher than 1100 kcm, take 12.5%. All this is in this article. Grounded conductor. So how do we size it then? In our situation, it's easy because we have 500 kcm. The same thing, table 250.66, and this will be the same thing, 1 aught. More, it could be bare, insulated, or covered. And I want to remind you for the system bonding jumper, guys, the conductor size, if conductor size more than 1100 kcm, then I bet your person will be very proud of me here. Then you take 12.5% of phase conductor. Phase conductors. This is what you guys know, 12.5%. In our case, we're not higher than 1100 kcm, so we don't have to worry about this. Five minutes break if you guys don't have any question. I have one more example for you. Any question, guys? Okay, let's go ahead and start. Where am I here? The example that we did is typical for low voltage. Oops. The example that we did is typical for any low voltage transformer like the one that you're looking at. Typical. So I don't need to give you 3-4 more examples like this. All what you have to do now, just go change the kW here into 500 kW, 1000 kW, and do the math again. Same calculation. What I'm going to change this time, I'm going to have, if you look at the voltage, both of them are less than 600 volt. I need to put one example where the voltage on the primary is different, because its calculation is going to be slightly different. So here's the second example that you, my friends, have. This one, I want you guys to look at this transformer. You have, by the way, this is the back of the page that you have. The back of the page, everybody can see it on the back of the page. You have a transformer, 1500 kVA. The primary is 4160. The secondary is 48277. And I need to find the same 6 things. The only difference between this example and the one that we did before is the primary is higher than 600 volt. That's it. That's the only difference. Really, everything else stays the same. Because of that, though, I want you guys to go to, since we answer to the Bible, we're going to go to the NEC code book and look at the table that handled this. Okay, so everybody knows the 450.3b. We just went there. Right before it, guys, there's another table that says, this table is 450.3a. 450.3a, if you can look at 450.3a, a couple of things you have to pay attention to. This is if the voltage is more than 600 volt, and it's more, but you have to understand if it's more on primary or secondary or both. So you use this table if the primary or the secondary or both are more than 600 volt. Does that make sense? If one of them is more than 600 volt, you use this table. Okay, an example of this. This is how your system should look like. I have a delta. I'm going to use a delta here. Here's a delta here. This delta is 13.8 K. On the other side is a Y, and this Y is 480/277. Okay? Should this table apply to this? Yep, because one of them at least is 480. Yes, sir. Make sense? Okay. Now, how do you use this table? The most important thing is the primary. Can you just see if the primary over 600 volt, then your default is always to any location. I'm highlighting the default, by the way. Always any location, you default. Any location. Default is not, this is also your default. Is the impedance is 6% or less, unless you know otherwise. That's a default. Okay? And you have the option of having a circuit breaker or a fuse. Most of the time, the default is a fuse, and the multiplier would be what? 300. And I want to remind you of note number 1. And if you read note number 1 here, it says, oh, by the way, if it's not a standard, what do you need to do? Go to the next stop. Can you guys see that? If it's not a standard, go to the next size up. That's on the primary side. On the secondary side right here, you have 2 options. Either you could be, the secondary could be over 600 volt or under 600 volt, right? So over or under. Most of the time, default usually, in your case, since you guys doing building, most of the time default is that the secondary is less than 600 volt, most of the time, but it could be also more. And then we're using either a fuse or circuit breaker, doesn't matter, my multiplier is 120, and pay attention to the 1%, the note number 1, which tells me if you don't hit a standard, what do? Go out. That's your default. So what's my default then? Your default when you size is really the first row here. That's my default. And most of the time, this is a default. Most of the time, this is kind of the most common. But you could use any of these. Okay? In my case, if you guys look at the transformer here, I know this is exactly what this transformer should be. I will use the list 600 volt or less here, and the primary is a fuse. Can I have a circuit breaker? If I use a circuit breaker, actually, it's 6 times. Okay? Now, supervised location only. if you are an industrial plant and you have very smart, competent group of people maintaining and troubleshooting the system, they allow you different multipliers. You usually don't default to this unless you know that mostly industrialized location. They have a group, guys, the maintenance electricians sitting there maintaining the system, and you can size based on this system. What's your default though? Here's my default. Unless you know otherwise. Cool? The impedance is default, you know the impedance default and so forth. There's a few differences. I don't know if you can see. Here's the same. There's a few differences in the multiplier here. Here's the same. This is few differences. There's just a few places where the difference is actually impedance-wise. Look at that. This is my favorite. It's supervised location. They allow you to put 300% versus 600% non-supervised. Not always. I can have a transformer that 13.8, 4160, then I have to go down to here. Right? But these are the most common that you're going to encounter. What I'm highlighting is the most common. Default, most common. Most common in my book is 90% of the time where you guys are going is going to be in this situation. Don't think I have anything. Any questions about this table? Everybody knows how to use it? Right? So let's take a snapshot of that and go back to the example. Now we know where we got the info from, and we're going to go back into my example. Okay, Audible, here's my example. Everybody has this, guys, the example that we have. We have a delta Y transformer. My delta Y, and we're going to go size the stuff for this Mr. Delta Y transformer. We're going to go size my stuff for that baby. Okay? So, primary current. Let's go to, there you go. Here's my transformer. The first thing you need to do, if you want to size the transformer, now I know Phil is going to say, where did you get that one? Chad, the calculation. Take this, Phil. I bet you've never seen that. 215.210 branch circuits. I don't know if we have feeders for that. Okay, let me give you the reference for this. This is high voltage. The primary is high voltage, completely different. 215 dot. If the reference is 215.2, 215.2A, no, B. This is where you find this reference, 215.2B. I know nobody have used that one. Unless you size medium voltage, you've never been there. 215.2B. If you guys go there, it will tell you you have to size it based on 120% of the designated load. So that's what we're going to be doing. Basically continuous load. Nothing really, no gimmicks on that one. So let's go take the I primary equal the 1500K divided by 1.73 times 4160 volts, right? And if you do that, you're going to end up with 208 amps. This is the amazing part on the high voltage. If you look at this 1500 kVA chair that you're pulling only 208 amps, yep, because the voltage is high. Higher voltage, lower amps, more efficient system. Any questions about the I primary? That's a current that's coming in. To size the conductor, actually, piece of cake, Chad, based on this, you're going to go to 1.25. Why 1.25? I'm assuming the load is continuous load. By the way, if the load is non-continuous load, or it's factored in, you don't multiply by 1.25. So, but just disclaimer here. Multiply by 208, that will get you a healthy 260 amp. 260 amp. Okay? Well, There's a little issue here. I want to take my 260 amp. Which table am I going to take it to? I want to remind you before you answer to look at the voltage here. Can I take it to 310.16? 310.15b16? No, 310.15b16 is limited to 2000 volt, guys. Is this 2000 volt or less? No, so I can't go to 310.15b16, Chad. I'm stuck. So where am I going to go to size that cable? That's where I want you guys to go quick into table 310. That 19. They change them. Let's go to this table. So to size it, I'm going to go run into the NDC code book for help here and find a medium voltage cable that can carry this baby. To help me with this, I'm going to go back to Article 300, 310. Okay, if you guys, I know few of you probably have used these tables, but in the back of your book, if you look at this, actually, this is where you size conductors higher than 2000 volt, right in here. 310.60. That's where you size conductors for high voltage. 310.60. Okay, 310.60. Though you need a table. The table that we're going to be using, guys, I'll get back to it. So we're going to have let's say we're coming underground, and we're going to be using conductors. 310.18. They changed the numbers on me. So a bit of insulated conductors, temperature rating. Okay, we have here medium voltage. Let's go to detail. I want one that give me details. Okay, here you go. Hold your horses. Of 3 single conductor underground electrical ducts. There you go. That's it. I want to go to table 310.60C77 and basically of 3 single insulated copper conductors in underground electrical ducts, 3 conductors per electrical duct based on ambient earth temperature of this and all this good stuff. And detail 1. Okay, so let's highlight this table and stop right here. Take this. This is the table I'm going to go, but I want to highlight a few things, guys. Number 1, what's the voltage system that we have? What's my voltage system? 4160, right? What's my voltage system? 4160. So I'm right in here. This is up to 5000 volt. That's where I am. What type of insulation am I going to be using? That's a medium voltage. If you don't know, what I'm writing is a default. You don't know, your default is MV90. MV90 under the 90 degree, that's your default for medium voltage. MV90 unless you know otherwise. MV90 unless you know otherwise. Okay, and detail 1, I'll show you detail 1 in a second here. Detail 1. Okay, so looking under this column, because of the voltage and because the default, what was the amp that we came up with? We came up with 260. 260. Okay, let's go down here. I need 260, 250. So what's my conductor size? What's my conductor size? Can you guys read that? Right here? Anybody? 4R. Thank you. My conductor is 4R. Why 4R? Because 4R can give me 260 or more. 4R. So what we're going to write it, you need the 3 conductors, number 4R MV-90. This is actually, instead of THHN, this is a medium voltage conductor, fully shielded medium voltage conductor. MV90, 90 stands for the insulation rated for 90 degrees, so they can get as hot as 90 before smoke starts coming out of it. Unlike low voltage, where we size based on 75 maximum. This is very major change. I'll get back to this. I will get back to this in details as we go industrial, guys. Any question about this? Now, Rob, if my voltage was 13.8, can I default to this? Where should I go? 13.8. You're going to go to this side, right? Because 13.8 is right between these two. So my voltage that I used for this system was 4160 volt. That's why I defaulted to here. If my voltage was 13,800 volt, where should I default? I'm going to be defaulted to this. Okay? All right, so look at that. This is 3 single insulated copper conductor in underground electrical ducts, 3 conductors per electrical duct, and some temperature limitation and so forth. So that's the assumption is. Any question about this, guys? Why did I go to this table, not to any other table? Because, my friends, this table is the medium voltage. So 310.60 C77. 310.60 C77. They changed it since I did that presentation. Any question about this, guys? Why did I pick this one, not any other one? You can look at them. We'll go into details of these medium voltage tables at a different time. But this is the most common one, guys. Underground duct with cables, medium voltage in it. I want you to pay attention to this before I leave. Can you guys see where it says detail here? Detail 1, this table is based on detail. Can you guys see detail here too? This is for aluminum, I believe. Yeah, this is for aluminum, this one. We don't want to use aluminum. Detail 2, can you guys see detail 2? They go by how are you going to put these conductors in the ducts. Based on how you put them in ducts, they're going to carry different amps. So I'm going to go and show you what detail 1 looks like. Now remember, 3 conductors in 1 duct. Okay, so I'm going to take a snapshot of this. Go back to the details. If you look at the details, here's where the details come from, guys. Detail number 1. Can you guys see the detail number 1? Right here. Here's detail number 1. Detail number 1, it will tell you, I have a conduit. Inside my conduit are 3 conductors. This is conductor 1, conductor 2, conductor 3. That's it. And what I'm going to do with this, I'm going to put it in a concrete encased. I put concrete inside this duct. If I put the 3, each one of these 3 in my case, each one of these was 4 aught MV-90. Each one of them shielded, fully shielded, medium voltage, in 1 duct, encased in concrete. And here's the dimension of the concrete. The whole duct is 11, almost a foot by a foot. Imagine a foot by a foot, guys. Concrete encased duct. So, and inside it there's a pipe, and carrying 3 conductors, not 1 phase, 3 single conductor cable, they call it. Any question about this, guys? Why detail 1, not detail 2? Detail 2, you can have 3 circuits. I only have 1 circuit, right? 1 circuit right here. Any question about these details? It becomes big deal if you do medium voltage. I encourage you guys, what I'm going to do, if they approve it, I'm putting a 2-hour class about medium voltage for the electrical Midwest Electrical Expo that's coming in March. You guys are going there. So I encourage you to come to my class. We'll do more on that. So every 2 years, North Central Electric League put a big gathering, 10,000 people show up. So I'm going to do a presentation about the medium voltage. So we'll do it at that time. Anyway, that's good enough for you. Questions before I leave this and go back to my snapshot of this. Go back. Okay, now knowing what we know, let's go size this cable. So which table was it? 310.60. They changed it on me. You go to 310.60
C7.
Thank you. C77. Is that? Yep. Thank you. And what was the size? 3 conductors. Why 3? 3-phase number 4/aught A, W, and G, and MV-90. You have to put the MV-90. This is not THHN. These are no THHN. That's it. That's the only difference from what I've done the example before. Really the only difference. Everything else, I've done it in the first example, excluding the fuse though. Any question guys about the cable? See how nice and easy the cable is? You got yourself a shielded cable, MV 4-aught. I have a few of them in my office. I have 2 of them in my office. If anybody will look at how thick and big and shielded and so forth. Okay, let's go find 2. So here's the tables that we went to. Okay. Let's go back to primary overcam protection device. We're going to do the primary now. Let's do the primary overcam protection device. The primary overcam protection device, guys, 450.3a. You're going to go to 450.3a. And I took you there. What was the multiplier? Anybody remember? It was 3 for overcam protection device. What type? We wanted to know what type, right? So first, what I think it's fuse for a fuse. Can you guys see it right here? Okay, see for a fuse, my multiplier was 300, right? 300. So that's piece of cake, Chad. So 300 times, what was the amp for that baby? Oh boy, the amp for that boy was 208, right? The amp was 208. Okay, here you go. 208. If you do this math, you're going to end up with 624 amps. And guess what? You're going to go to 240.6. And from there, Ashley, if you read the note number 1, it says if it's not a standard, go up. You can go up. You don't have to go up. You can go up. So what's the next standard? 700 amp. And if it's not a standard, what do I go? I can't emphasize that. I always write it down. If it's not standard, you go up. It's not standard, you go up. That's my symbol going up. Questions? 700 amp fuse. And by the way, what did we use here? We're using a fuse. Typical in that application. Fuse. Not a circuit breaker. If it was a circuit breaker, it's 6 times that number. Okay, the last thing is the secondary conductor. That's piece of cake now. Secondary conductor. Secondary. Any questions about the fuse? So you're going to buy yourself, Ashley, and Nick, my friend, a 5 kV 700 amp rated fuse. 5 kV. That's a big boy. Okay. Secondary is piece of cake. Take the 1500K divided by 1.73 times. What was the voltage in the secondary? 480. And that will give me a healthy 1806 amp. The 208 amps on the primary will be transferred into 1800 amps on the secondary. Now you understand why we use a high voltage. The difference. Okay. So we need to size the conductor though. That's not enough, Chad. 1.25 times. Okay, now where would you find this one? 215.2A. Because A1. Thank you. A1. That's what it tells you to do. It's a feeder. Take this by 806. What would that give you? That will give me 2258. 2258 amp. Now disclaimer, I'm assuming that these, my assumption, guys, big assumption, that these are continuous load. If it wasn't continuous load, I can easily size based on 1800. Okay. So here's my question for you guys. I don't know about you, but I can't find a conductor that can carry 2200 amps. So what do you need to do? Thank you. Now we get into the parallel business. I have 5 sets here. I'm going to parallel now 200 and 258. I'm going to parallel by 5. Could I parallel by any number? Yeah, but number that makes sense. Always hover around the 500 kcm when you parallel. This will give me 452 amps. Now you know why I parallel 5. Why the 5? Because it gives me 4. And if I take this one to 310.15, B16 under 75-degree column, now actually this is a low voltage conductor, right? I can go to 310.16, 15 B16. And based on this, my friends, based on this one, I'm going to carry how many conductors? Let's go to my conductor. I don't want to do the rating for the neutral here, guys. I don't want to do the rating for the neutral. You know how to do it. I'm going to carry full neutral, but you should do it the neutral though. I'm going to carry 4 conductors. and I have 450, 700 kcm, and insulation is THHN. And how many sets? 5 sets. 5 sets. 5 sets. 5 sets. If I want to size the neutral properly, what do? You take the first 200 at 100%, the remainder, cut them by 75 and size your system. Any questions about that? 5 sets. That's a lot of wire. Can I go to the fourth, guys, to find the overcome picture? Yes, sir.
Who decides the size of the transformer?
Well, ultimately, there are 2 types of transformers. One, you own and operate in your building, and one, the utility own and operate outside. If it's the utility transformer, they decide it. If it's your transformer inside your building to take the 480 to 208, you decide it. How do you size it? I'd go this one next in the industrial, guys. You add all the loads you're going to feed from a transformer, and then you can find a transformer that can give you this load or higher inside your building. How does Excel size your transformer? You tell them what's the service. Remember the service calculation that we did? We came up with 500 amp. 500 amp, Excel will take your 500 amp most of the time and say, okay, those architects, engineers, they think they know what they're doing, but they really don't. So what they do is they shave it down, cut it by half or between half to 75%, give you what you're looking for. So if you're asking for a 500 amp service, they give you a transformer worth 250, 300. Taking into consideration that your load is oversized for safety and all this good stuff. For them, guys, you throw a transformer there, they overload it momentarily, not a big deal. They can overload most of these transformers 33%. So anyway, so they decided, long story short, if it's Excel. Okay, let's do number 4. Secondary overcome protection device. It doesn't matter actually if it's a fuse. This could be a fuse or circuit breaker. Really doesn't matter in this calculation for the secondary. Right? The secondary does not matter if it's a fuse or circuit breaker. So the multiplier in either case, it's going to be 1.25 multiplied by the full load amp that we came up, 1806. That will get me a healthy 2258. And I'm going to take the 2258, take this one to 310 dot, what? Not 310. 240.6. What's my next standard overcome protection device? 250, 4500, 4500 amp. My next overcome protection device size is 2500 amp. Any questions about this? So that's my my overcome protection device. The second one is a system, separated drive system. This is rounding. What did we say? The same. That will be 250.30 some. Anybody remember the 250.30? 30 what? A5. Thank you. Change it 2011. A5. You want to go back. If you go to 250 and also table 250.66, you guys go there. Since we parallel though, how many runs do we have? We have 5 runs. You take the 5, multiply it by 700, equal 37, right? 3700 kcm. You take this one to 310 dot, not 310, Chad, 250. You're going to take it to 250.66 table. And if you guys take it there, the maximum that you can get anyway is 3-aught. So one conductor, 3-aught, cover, bare, or insulated. Cover, bare, or insulated. Doesn't matter. 3 out. That's as large as you can get. No exception. No exception. Any question, guys, about this? Any questions? The last thing I'm going to do is the system bonding jumper. Same calculation for system bonding jumper. Did you write the 37 here? Did you, Nick, did you write 37? Somebody wrote it.
Yeah.
The way I gave it with the 7. 5 times 7 is 35. 35, 7, KCM. Doesn't change the outcome. Okay, let's do the grounding. Everybody knows what this is, the one that's going directly to the steel of the building. The last thing, guys, number 6. Number 6 is, they call it system bonding jumper. System bonding jumper. Okay, this baby is coming from 250 dot, what was the article that I referred to you guys? 250 dot, the same article like the grounding residual conductor, except 250.30.30A. What did he say? 1 and 3. If you go to A, it's all talk about bonding jumper and so forth. Okay, in this case, and also table 250.66. If you go there, it will tell you take the 5, multiply it by the 700 kcm. They'll give you 7,500 kcm. Is this more than 1,100 kcm? Your answer here is yes, right? Then this is what you need to do, right? It's more. Then you take a 12.125, 12.5% multiplied by 75000, right? So I have an extra 0 here. So 7,500 kcm. If you do the math on that baby,
It's 35 jet.
it's something wrong.
35,000.
I didn't write the 7. 3,500 kcm. 3,500. So we multiply by 0.25, you're going to end up with 48. I have 4, what am I going to check? 38 kcm. Make sure you take this one to chapter number 9, table number 8, and that will translate you into the next standard, which is 1 conductor 500 kcm. Cover, bare, or insulated. Right? Table 8 will get you that baby. Table 8 will get you that baby. Any question, guys? Phil, did we do any mistakes here? This,
How many sets would you draw hard?
Oh, all equal. Let's draw that. We have 5. 1, 2, 3, 4, 5. So each one of them is going to have 1, 1, 1, 1, 1, and the second one 1, 1, 1, 1, 1. Did I miss any? And we're going to have a black too. 1, 1, 1, 1, and 1. And the neutral all the equal is going to have 1, 1, 1, 1, and 1. This is how your systems look like. 5 sets of conduits. Each one of them is carrying 4 conductors, 3 phase and neutral. In my case, it's full neutral. really you should derate it, but I just don't do the math. You guys good at doing the math. You can take the 200 aside, cut everything higher than 200 by 75, and parallel 5 sets. So these are, I don't know if that was your answer, I'm just exaggerating here. This is your 4 conductors of 700 kcm, and I'm going to say THH10. I can go find you a conduit based on that one. NXC, THH10, 700 kcm. Let's use, where are we coming? We're inside the building, so let's use EMT. Let's use EMT. Anybody can get me the answer for that one? EMT 700 kcm. Well, I don't know EMT if we can fit that baby. That goes all the way up to 500. We might have to go to rigid to get 600. As long as I'm not pulling these conductors, I can make them as high as I could. So, any question, guys? Okay, so, any questions? Let me see, PVC. I'm going to go now, you made me curious, all people. So, let's see, the first conduit is EMT. Wire electrical and tubing, THH10. Let's guess THH10, what size? 700. Oh, I got it. 700, that will give me 3.5. 4 conductors, 3.5. So that conduit here is going to be 3.5 EMT. I'm putting an EMT. Can I put rigid? Yeah, bring it on. Previous EMT. Why EMT? Because if I'm THH10, I'm indoor. If I'm indoor, most likely I'm EMT. Any questions about this? So that's what chapter 12 talks about, transformers. We will visit this as we move into the industrial, because that's where we use a lot of transformers. So we start doing a couple of other things. I'm going to stop right here, but what I'm going to do tomorrow, I gave you another piece. Everybody have the other piece. There are two more pieces here. So I have question number 1. I have an example, guys, I'm going to be using tomorrow of a 13.8. Oh, is this the same? Okay. No. How many pages did I give you guys? 2 pages? 1, 2, right? 2. Okay. So that the one that doesn't have anything in the back, I'm sorry, I should have numbered them. This is, I'm going to go over. The example would be 13.8. We'll do the same thing for 13.8 tomorrow. And the second example is the best. That one, guys, we're going to have a primary and a secondary of transformer. We're going to size a receptacle panel to match the transformer. Now we're getting into sizing a panel that matches a transformer. So these are the 2 examples. I'm going to do them today, tomorrow before the party. So I don't want to overwhelm you with it, because I need your full undivided attention. Okay, and you guys have a picture of it. I have way at the bottom, if you have a chance, guys, review the bottom one. The bottom tells you the 25-foot tab rule, 25 or less foot tab. That's what we're going to be using tomorrow when we size conductors and overcome protection device for a receptacle panel fed from a transformer through a high voltage panel. So, anyway, any question, guys, for Chad? Any questions? Every time, guys, we meet with the PAC committee, I know some of you say, Chad, this is probably complicated. Every time we meet with our PAC, Program Advising Committee, they tell us we can train people how to draft. Drafting is easy. I can get you with anybody to draft. What we want people to know is the design aspect. This program is designed primarily. Now, we're not drafters only. So that's why we emphasize on these things. Even though you might not encounter a lot of them at the high voltage, you will be a better designer by knowing what we're doing, really. Okay, that's all what I have.